monitoring system using distributed fiber optic sensors, which we developed here at CSIC, to monitor the axial shortening of tall buildings as they are being constructed. This is a project which we carried out in collaboration with our partners Multiplex, WSP, and Kerry's. Principal Tower is this building here on the right, and it's just about to be completed now in central London. It's a residential building, 50 stories tall above ground. It's about 163 meters, plus two basement underlying it, two basement levels underlying it. The structural system seems pretty standard. It's got a central reinforced concrete core, 12 perimeter columns, also reinforced concrete, and post-tension concrete slabs in between. However, there's a big complication when you go underground, because about a third of that building is built over a railway tunnel, which was excavated as part of the project. So that section there in red is all resting on the roof of the tunnel. So the roof of the tunnel is about 1 meter thick, for highly reinforced concrete, and very deep transfer beams shown in blue over there. So moving on to the problem that we're trying to solve here, or how the problem that we're trying to measure, which is axial shortening. For those of you not familiar with this, axial shortening is so when you've got a building that's being built in floor by floor, you've got a number of load-bearing elements, vertical load-bearing elements, columns, walls, etc. And from the moment that those elements are constructed, they start shortening. They shorten due to a number of effects. You've got the elastic effects, which is due to the additional load being built on top of them, hence the shortening. But then you've also got the material effects, which are inelastic, and that's a combination of a long-term creep and shrinkage of the concrete. The problem here, more than shortening, is differential shortening. So each of these elements shorten by a different amount, because the shortening is related to the size of the element, the amount of reinforcement, how much load it has. So typically the columns and the more slender columns tend to shorten more than the core walls. So if you don't account for this during the construction, in advance of that shortening happening, you end up with something like this. Your building floors are sloping and they're not at the right level. And that would lead to additional forces inside the beams and the slabs, and it also could lead to damage to the non-structural partitions and the facade cladding. So what tends to happen is that the designers try to predict how much shortening is going to happen in each individual element at certain stages in the construction to enable the contractor to account for that. But the onus is placed on the contractor to get it right, because these predictions are based on a lot of assumptions, and they're done using empirical models. So the contractor invariably has to measure how much shortening is happening during the construction and the floors that have been constructed already to be able to adjust those predictions. And that tends to take place traditionally using surveying techniques, where a survey is sent once every few weeks to take spot measures on a few of the columns or walls at a number of levels, say one in every 3 or 4 levels. The problem here, of course, is that you don't know what's happening in between measurements in time, and you don't know what's happening at the unmeasured floors. So the contractors and the designers approached us to design a monitoring system that would enable them to monitor the shortening of the building as it is being built continuously. So a slight sidetrack for those of you not familiar with distributed fiber optic sensing, just a quick slide here. This technique enables us to use an ordinary optical fiber, which we can embed or attach to a structure, and that fiber becomes a very long sensor throughout which we can measure strain or temperature at any point along that fiber. This, I make the analogy to the nerves in our body, where the nerves in an arm, for example, are not just transmitters of sensory information, but are also sensors in their own right. Back to Principal Tower. So with the contractors and the designers, we selected 4 locations in the building, 2 columns and 2 points in the core wall. And these were instrumented with fiber optic cables, a pair of fiber optic cables in each of those locations, 1 cable to measure temperature and 1 cable to measure strain. We attached the cables to the bottom of the rebar at the ground floor, and from then on we trained the contractors' operatives to install the cables as the building rose. We prepared enough cable length to go up to the top of the building in each of those locations inside cable reels, so to make it simple for the operatives to unreel the cable as the building rose level by level. And those cable reels were incorporated within the jump form rig of the tower. At the same time, we were monitoring the strain and temperature of those instrumented columns and walls throughout the construction. So starting from before the construction and lasting for about 20 months, we were continuously taking measurements every half an hour of strain and temperature. And that gave us, over the whole height of the building, about 3,000 measurement points of strain and temperature from a single measurement location. Those data were transferred automatically to an offsite server. They were post-processed, changed into axial shortening of each point along the height of the building relative to the ground floor, and communicated with the contractor so that they could review their predictions and adjust the levels going forward accordingly. And I'll have a little breather here. I've put this time-lapse video of the construction. You can see the jump form rig there at the top, which had the cable reels inside it. Those are being unreeled every time the level goes up. And you can see now the facade cladding lagging about 10 to 15 stories behind the construction. That's quite typical. And that's a critical stage at that particular level when the facade is going in, because the facade needs to be put in, taking into account the final level of the building. So you need to take into account how much more shortening that level is going to experience. Otherwise, if you don't leave enough tolerance, your facade is going to be damaged. I think that's graphical enough. We can move on. So 1 year of data. This is the first year of monitoring. The building was about level 30-something, about 34 over here. And to show you what these graphs represent, this is all the data compressed into 4 graphs. So just to show you what this data represents here, if I take that little section of data, 1 month of data, from one of the columns, if I take the building and flip it upside down, each of these lines is representing the axial shortening of the midpoint of a particular level relative to the ground floor. So it's cumulative axial shortening. So going back to our data, we've got the data we measured from the columns at the top and the walls at the bottom. And we can pick out several interesting features, and I'll just highlight a few here, and I'll take these 2 months of data as an example. So starting with the columns here, if we take into account elastic and elastic shortening, we would expect the shortening to be increasing linearly, because we're adding more floors regularly. The concrete is creeping and shrinking with time, so we would expect the shortening to be increasing linearly. Incidentally, shortening here is shown as negative axial displacement. You probably got that already. But we can see here that there are these fluctuations in shortening. It's not quite linear at all. And those match very precisely with periods when high temperatures were measured. So we get a big influence from thermal effects. Now, remember, we're also measuring the temperature of the concrete with the other fiber optic cable. So we can estimate how much of that shrinkage is due to thermal expansion and contraction. And if we remove that effect, we will end up with what we call mechanical axial shortening. That's just due to the elastic and inelastic effects. And that is much more linear. The problem here is that the designers would have predicted this, because the thermal effects are not taken into account during those predictions. But what's really happening is that. And if we compare the two, say for one of the periods where there were high temperatures, we can see that the shortening was reduced or increased, depending on whether it's high or low temperature, by as much as 30% due to thermal effects. And this was one of the big surprises that came out of this monitoring. Something we can also see here, if you look closely, we've got column 8 is shortening about 10 to 25% more than column 9, depending on which level we're considering. And that's what I was referring to in terms of differential shortening. In this case, it was expected, because the cross-section of column 9 is much more slender of column 8 is much more slender than of column 9. And even though column 8 is taking about 10% less dead load than column 9, the shortening is more pronounced due to the smaller stiffness of the column. If we compare that to the walls, then this is the shortening of the walls shown to the same scale as the columns. we can see that the effect is much more pronounced. So the contractors have to build their slabs in a kind of upward banana shape, so that when the columns shorten as much as they need to, all the slabs come level and flat. And one other small thing I would like to point out here is this seemingly insignificant little spike at the top over here, which we recorded around November of 2016. And when we were, the building was about 5 or 6 floors high by then. And when we were trying to investigate why this happened, you can see that the shortening suddenly doubled over a short period of time. We were looking at the CCTV images that were being recorded of the construction, and we noticed that at that particular time the jump form rig was raised from one level to another. And what we suspect happened is that when the rig was raised and then lowered into place on the holding pins, perhaps in that particular location, because we only recorded this effect in that piece of the wall, the piece of the core wall, when the rig was lowered, we suspect that perhaps it was lowered with a bit of a sudden loading, which caused the dynamic load would have caused a sudden squashing of the wall in that particular location, which then started recovering immediately afterwards, but it still resulted in about 0.5 millimeter of residual shortening. Remember, here we're talking about 0.5 millimeter over 6 stories, so it's very little still. You can see the power of this monitoring technique, the amount of insight that it can give you. So that brings me to the end of my presentation, and in conclusion, I can say that this distributed fiber optic monitoring system that we've developed has allowed us to measure the strain and temperature, and hence the displacement or shortening of the building with a very high spatial density and high temporal density, continuous monitoring, and also monitoring along the whole height of the building, which before this was not possible at all. And this has allowed us, in the case of Principal Tower, to gain insight into thermal effects, differential shortening, and also to observe what effect sudden loading has on the shortening of the building. And with that, I'd like to thank you for your attention.